And now we have to move to the second talk of this section. It's a paper by Gabriel, Hondet, Frédéric, Blanqui, Gilles, Dowek, and Emilie Grienenberger and François Thiré. The presenter is Gabriel Hondet. Some actions for mathematics. And okay, please, you can share your window.
Right. So,
Gabriel.
Yes. So, as the title so suggests, this presentation will present some.
Give it some time. All right. Ready.
Can you see my slides?
Now, yes.
Okay, right. Okay, so hi everyone. So in this presentation, which is in fact quite general, we present some axioms that can be used to develop, so to perform formal developments of mathematics. So first we make this to answer what we could call another crisis of the universality of mathematical truth. And to evince this, we can wonder first whether we have a proof or what proof of the four-color theorem we have. And in fact, we don't have any proof. We have a Coq proof of the four-color theorem. And similarly, we have only a whole light proof of Hale's theorem and a PVS proof of the correctness of the 3R3G algorithm. And what we can deduce from this fact is that the truth of the four-color theorem depends on the implementation of the logics that is implemented by Coq. And the same goes for Hale's theorem. Its truth depends on the whole light implementation. And so we say that it's yet another crisis because we already saw that such kind of things with, for instance, the apparition when constructivism appeared, and some people did not agree on what was a valid proof or what was a proof at all and what wasn't. And so here in our case, we may have, we can already describe some kind of solution or a first step towards this solution, which would be to have a common language or common syntax between these proof assistants. So here I just mentioned Coq, PVS, and whole lights. And so for this, we have already a tool which we call a logical framework that can be described as tools to define logics in general. And so they seem to be well suited for this task. And hence, when the developments are translated in such a logical framework, we can analyze the axioms which are used in these logical frameworks and compare them. So we will first describe what are logical frameworks are. And so we already know, for instance, as logical frameworks, the predicate logic or ecumenical theories or lambda prolog or Edinburgh logical framework. And here, in our case, we are interested in the lambdaPi-calculus modulo theory. So in brief, lambdaPi-calculus modulo theory is like Edinburgh logical framework with arbitrary reduction rules. And so in our team, so we use an implementation which we call deducti, and with which we can try what we developed in the lambdaPi-calculus modulo theory. And so we can mention some features of the lambdaPi-calculus which are essential. So we have bound variables, like in lambda prolog, Isabelle, or the Edinburgh logical framework. We can express terms as, we can express proof as terms, like in the Edinburgh logical framework. The deduction and computation are mixed, like in deduction modulo theory. And we are both classical and constructive, or can be only one of them if we want, but we can be both, like in ecumenical logic. And so we can already say that this framework, in this framework, we can in fact express several theories of several proof assistants, because past developments have already shown it, so that we can express simple type theory, which is the basis of, for instance, HL4, HL light, Isabelle HL, etc. We can also express the calculus of constructions, which is the basis of Coq, Matita, and Lee. But we can also express the simple type theory with predicate subtyping, which is the basis of PVS. But we say so that these proof assistants share a common syntax, the syntax of the lambda-Pi-calculus modulo theory, but perhaps they have more in common. And we hope that they have more in common. And in fact, we can sense that they have more in common because each proof assistant, for instance, proves that many axioms on, for instance, arithmetics. So they have a bit the same contents, or they share some contents. And so we may have the idea that they express at least the same thing partially. And so the goal of this talk is to provide a theory which we call U for universal, which provide axioms that are shared between these proof assistants or these logics. And so what we call an axiom in the lambda-Pi-calculus modulo theory is either a symbol declaration with a type or a computation rule. And in fact, an axiom can also be a grouping of a symbol and a computation rule. And so the idea is that all the proof assistants we have mentioned before, so Coq, PVS, HL Light, Isabelle, etc., have a theory which can be encoded as a subtheory of the theory U. And by subtheory, we mean a theory which is made of a subset of symbols of U, and such that these symbols have some property of closure between them, so that they behave properly to define the theory. And so now we'll introduce how this theory U is made and how we use it. So first, we must remember that the lambda-Pi-calculus modulo theory is a weak framework in the sense that it has very few things that are built in the framework or native. And as such, in these slides, only what's in black in the types are native to the lambda-Pi-calculus modulo theory. And so here we see that we have the constant type, which is the type of types. And we have the arrow, the dependent arrow. And we will also see the dependent product, which is noted pi. And so to begin with, so the symbols in blue are the theory U. We define the constant set, which is the symbol or the type of encoded sorts. So the sorts of the logics are terms of type set. And for instance, we can declare iota, which will be a sort of the logic we encode of type set. And we have a function EL, which maps these encoded sorts to lambda-pi types. And so we can also say in the language of the logical frameworks that EL is a family of type indexed by the encoded sorts. And now we define the proposition. So we have prop, which is the type of proposition. So this is a lambda-pi type. And we have the implication. And we have the for all quantifier, and that we see that this quantifier so it quantifies over elements of type set. And as such, we can't yet quantify over proposition because the proposition is not an element of type set. And so we see as well that we have a constant set of type. So for the sets and the quantifier which quantifies over sets. But we could also have translate each type of the encoded logic to a type of the lambda-Pi-calculus modulo theory and have one quantifier per type. But so we would have a setting like this with I1 and IN being types of the lambda-Pi-calculus, which would be also the type of the theory we want to encode. And we would have as many quantifiers as we have types. But we decided like to abstract a bit more and to have the types encoded as terms and the quantifier taking the encoded type as arguments. And so we have we can have an infinite set of sorts of encoded sort, but only one quantifier for all of them. And in this slide, we can see that we have declared 6 axioms, and we can see the axioms, in fact, in between parentheses at the right of the slide. So now we see how we encode proofs in our theory. And we have 2 observations. So the first one is the Curry-de Broglie-Howard property of correspondence, which says that a proof pi should be of type the proposition proves. So say that pi is a proof of P implies P, we would like to have the judgment P of pi of type P implies P into our logical framework and into U as well. But this is not possible. Why? Because P implies P is a proposition, so of type prop, and prop is of type, and hence P implies P cannot be a type because it's not of type. So for this, we define a new dependent type proof, which is of type prop2 type. So it's, in fact, it can be seen as a function which takes a proposition and maps it to the type of its proof. Or it can be seen as a family of type, which is indexed by any proof. And so proof of pi ends being the type of the proof of pi. And so we can have the judgment, on the other hand, that pi is of type proof of P implies P. And then we have the Brouwer-Hating-Kolmogorov. So here we have two observations to make. The first one is that we use shallow encodings, and hence the functions that we encode from the logic we encode are translated as function of the logical framework. And that's why a function that we encode is translated as an abstraction. And so this function, lambda x, which is a proof of P x, should be of type proof of P implies P. And this is the Brouwer-Hating-Kolmogorov interpretation. And is this possible in our framework? Well, it is still not possible because lambda x proof of P x, because it's a function of the lambda-Pi-calculus, has type proof of P arrow and the arrow of the lambda-Pi-calculus, so a product proof of P is not convertible with proof of P implies P, or is not the same. But since we have arbitrary reduction rules, we can say that proof of P implies P is the same or reduces to the type, the lambda-Pi type proof of P to proof of P. And in fact, we can see that this reduction and proof can be seen as the Curry-de-Bruyn-Howard correspondence itself, because it says that a proposition can be interpreted as a type. And so we have the following judgment, which is true. Lambda x of type proof of P x is of type proof of P to proof of P, which is also of type, well, it can be seen also as type proof of P implies P. And so we have the interpretation. And in this slide, we only have defined one axiom, which is the declaration of proof, because we group the reduction of the implication with the declaration of implication, so that we have some kind of declaration of the symbol and some computational content of the symbol, this symbol grouped as one axiom. Next, we have the connectives. And so the first remark is that the U is ecumenical. So we have for each connective a constructive version as well as a classical version. And so, so we have two symbols because these two connectives have different meanings and different behaviors. And as such, we have two different symbols, just the same as we wouldn't have the same symbol for the inclusive or the exclusive or. And a second observation is that we use higher order definition of the connectives. And just for an example, the proof of top, so the interpretation of top, is equal or is defined by such this term, which is, we can see, just dependent products of the lambda-Pi-calculus. And the classical connectives are all defined using the double negative translation. And so we see that the proof of P implies classically Q is defined by not P implies constructively not Q. And all these definitions make 12 axioms in the theory U. And so what we see is that we have so far 19 axioms. So 3 for terms, 3 for proposition, 1 for proof, and 12 for connectives. And even though it may seem quite a large number of axioms, we must remember that on the one hand, the lambda-Pi-calculus is weak, and it means that many axioms are just here to define what is already built in some other logical framework. And for instance, many axioms are already built in the predicate logic. So in reality, it's not that much compared to all in terms of behavior. And now we can, that we have these basic axioms, we can define the axioms that allow to like develop interesting mathematics, we could say, and by that we mean the sets and functions. And for this, we just take back 2 ideas from simple type theory. So the first is to encode propositions as terms, and we define a constant omicron of type set, so it's an encoded type. And this will be the type of proposition with propositions seen as terms. And since it's the type of proposition as terms, and we have a function EL that maps encoded types to deducted types, and that we have already declared the type of proposition in lambda-Pi-calculus model theory as prop, we make the two equivalent. So the interpretation of the encoded type of proposition with the type of proposition, so with the rule Omicron reduction. And here we see that we can now quantify over proposition with our quantifier, since we can write for all Omicron. And next we have the type of function. So we have an encoded arrow, which takes two encoded types and yield another encoded type. And we can see again that we have a shallow encoding, because since we, as we said, we encode functions from the theory as function of the lambda-Pi-calculus, so lambda abstraction, we must map and the type of function to the type of function in the lambda-Pi-calculus. And so we map the type of encoded function, x arrow y, to the type of lambda-Pi function, so the element of x with the arrow of lambda-Pi to element of y. And here again, we group the axioms, we group the declaration with their reduction, and this makes two axioms. And we can define also more axioms. So dependency, just like what is used in code. So for instance, the dependent arrow or dependent implication in three axioms. We can have object level predicative polymorphism, like in whole light. Predicate subtyping, like in PVS, in 5 axioms. And the axiom of infinity in 4 axioms. And we can also have other features, more advanced feature, we could say, like proof irrelevance, universes and universe polymorphism, inductive types, and more. And so this shows that we have defined the basis, or the theory U is can be seen in several layers with the basis with the sets and functions, and on top of this we can define dependency and all the features we have defined there. And so the theory U can be in a way extended. And now we see the notion of subtheory, which justifies a bit that this formulation can be used in practice for interoperability. And a first question for this would be whether we need all the 38 axioms we have defined so far. And another question which may arise, and which is similar, is if we make a proof U with constructive symbol, can we be sure that the proof is indeed constructive? We mean by that, are we sure that the classical connectives won't appear in the proof during reduction, for instance, and won't pollute it, so that it becomes not only constructive, but there is classical connectives inside it. And as such, we must declare two closure conditions on a subtheory to be sure that we don't have such pollution that appear. And the first is that if you use the arrow, so the encoded arrow, you must use the symbols that are in the type, because you must be able to type the symbol of your subtheory inside your subtheory. And the other one is that if you must not have a subtheory must not have rewriting rules that produce symbols that are not in the subtheory. So we mean that if we have the classical connectives, well, the classical implication in the subtheory, we must have also the constructive one, because the classical implication rewrites to the constructive one. And so the notion of subtheory is defined by these closure conditions. So a subtheory is a subset of symbol of the theory U, and the symbol obeys these closure conditions. And so we have the following theorem as the subtheory, which says that if we have two theories, so T1 and T2, so sets of symbols, with T1 a subset of T2, if T1 is a subtheory of T2, so which obeys the closure conditions, and if pi is a proof of T2, so the big theory, which uses only the symbol of T1, then pi is indeed a proof in the theory T1. And in fact, this theorem allows to say that all the axioms are not needed of the theory U, since if we develop a proof which doesn't use, or which only use some portion of the theory U, we may indeed check the proof in that portion of the theory U and not the whole theory. And with that, we can in fact perform interoperability. And so here in this picture, we have drawn the several subtheory in U. And so we have grouped them in, well, according to their proximity and their use. And so, for instance, at the north, you have predicate logic. So first, constructive predicate logic and then classical predicate logic. So in the black boxes. In the orange boxes and on the toward the east, you have a simple type theory with the omicron and the encoded arrow. On the left, so on the west, you have the dependency. On the southwest, you have predicative polymorphism with scheme, element S, and the quantifiers. And on the southeast, you have the predicate subtyping. And so what we can do with our theorem is to say that if we develop a proof in Coq, so which is in the pink box, well, if we see that the proof doesn't use these three symbols, so the dependent arrow, the dependent implication, and the symbol for terms which depend on proof, then the theorem falls back to a simple type theory. And this means that a theory which is developed in Coq, not using these symbols, can be readily exported to the to HOL or HOL Lite, for instance, without any further work. And so finally, I'd say that to conclude, we define a theory U that's, we can recall it, that's made of 38 axioms, but we remember that all these axioms on the one hand are not necessary because of the subtheory theorem. And on the other hand, that many axioms are used in other logical framework or in other proof assistants, just that they are built in. And this theory U provides so such axioms that can be shared between all the proof assistants, and this axiom and the fact that they can be shared allows to compare the proofs that are made in the different proof assistants more easily than if each had their axioms, which is the case now. And so we finally have this subtheory theorem, which says that the interoperability is feasible in practice with such a setup. And finally, we hope that this theory provides a common ground to the proof assistants that will be used in the future to align the discussions and to evince the difference in the common points and to increase the amount of shared work between the proof assistant communities. And thank you for your attention.
Okay. Thank you very much, Gabriel, for the nice presentation. And let's see whether we have some questions now. I enjoy your last slide. There is some. Okay, no. I don't know whether it's related with the presentation, but okay, there are some technical questions. I am happy. Let's see whether someone write something in the chat, but I am happy you included, Gabriel, this slide explaining how this is this universal theory to think about the logics inside system like Coq, Hall, and also too much happy that you included PBS. But as far as I understand, you are working with a fragment, the sample type fragment of, so it's unclear to me whether you really included the dependent type theory from PBS, for instance. You included the subtyping theory from PBS, and what about inductive types? That's what's done, or if an extension you want to do in the future?
So we can say that in some sense, inductive types are done because we have already worked by PhD students, by Gaspard Thiré, that in fact, he translates some part of the Coq standard library to Deducti. So this is done. And as for PVS, you ask whether the subtyping is performed. Well, it's a question which can have a bit several answers because the subtyping can be performed in several ways. So the fact is that in PVS, it's performed, we could say implicitly, in a sense that PVS subtypes the thing by itself and the user doesn't see the subtyping. And in Deducti and in the theory U, here we have a way to perform this subtyping, but explicitly, sorry. And so we can see here in the slide that we have in fact the subtyping which is made by the first and pair elements, because these are coercions that can be inserted that can be inserted by the system, but in the theory U we must insert this coercion by hand, and so the subtyping is done by is explicit in the proof, we could say.
Mauricio, you are mute.
Sorry. Okay, there is another question from Jan Besai. Have you checked in how far practical development, such as MATCOMP with its implicit records, for example, introduce dependencies on axioms, which are there for practical but not theoretically necessary reasons? Okay.
The thing is, I'm not, for instance, for Coq, I know that our colleague had to deal with it. I'm not sure how he did, but I don't have any data available on this practical view of the translation of Coq. Sorry.
Okay. Okay, we have time for more questions. Jan say thank you. And well, I am really interested in the extension of this of the type system, no? And do you estimate how difficult will be that to enlarge to this work, including mechanization of dependency, intersection types, other extensions?
I think,
let's see.
In a way, it wouldn't be very difficult, and we know that several theories can be added to U as we could say as a layer or as a fragment, a new fragment, which already use some layers. So for instance, I think intersection types some types, for instance, can be added quite easily, because they are already a bit there with the predicate subtyping, since the predicate subtype is an instance of a pair type, a product type with a sigma type, we can say. And so it's really quite easy to extend the theory and to obtain a fragment which we must prove that this fragment is usable and corresponds to something and is covariant, but it can be easily used for further development.
Okay, thank you very much. Let's see whether I can accommodate another question by Thorsten Bisman. Thorsten, might you unmute your phone, please?
Yes. Yeah, thanks for the talk. So if I understood it correctly, you have kind of a common ground of all these systems. And did you consider doing the opposite, namely taking kind of the union of all the features that are there? Or is this even consistent? If you somehow try to combine all the features from the different systems?
Yeah, it may be the case that all the features of the theory are not consistent when taken together. But in a sense, it's not really a problem, because we intend to use only fragments of them. So we must not see that as a fatality, and just like we want to use fragments, and see whether a fragment is inside another fragment, or if the proof inside the fragment in fact falls down into another one. And so yes, well, we can see, for instance, in the theory U, it evinces the common ground between Coq and HOL, and the HOL system. So I hope it answers the question or the remark.
Oh, sorry. Thank you very much for your nice presentation, Gabriel. And then I have to move to the next